the bone marrow. Via blood, they go into the thymus gland or the thymus organ, and that is where they mature and perform and are able to perform the functions associated with T cells or the T cell mediated immune responses. Now, as they leave the bone marrow, because they are yet immature, they mature in the thymus, and that's why they have their name, the T cells, from the word thymus. So along with the T lymphocytes, there are other cells that share the same lymphoid progenitor, and that is the B cells and the natural killer cells. However, today we focus specifically on the T lymphocytes. Now, as their name suggests that they mature in the thymus, so from the bone marrow, we can talk about them as pro-thymocytes, meaning they are yet not yet mature. So the reason of this T cell maturation is to kind of like an educational system where they need to be trained to be able to differentiate between cell and the non-cell antigens. Okay, so those are some of the reasons why the T cells must undergo this kind of ontogenesis process, so that they can not become autoimmune, but rather help in defense against pathogens or some injured cells. Next slide, please. Now, what do you see there? Like I've mentioned, all the blood cells, they start from the bone or originate from the bone marrow through the process of hematopoiesis. And I've said like there are two important precursors. There's the lymphoid progenitor, and there is myeloid progenitor precursor, which gives to granulocytes. But we are looking at the lymphocytes genealogy, where you talk about the T cells, natural killer cells, and the B cells sharing the same precursor cell. But the rest you can find out uniquely how they finally mature. Let's move on. Now, the process of T cell maturation consists of the following three processes. We have the proliferation of immature cells. Now, this tells you that each T cell will undergo the cell division, and this will yield more daughter cells of the T cells. And that's why if you look at the number of cells that leave the bone marrow compared with the number of T cells that you find in the cortical region of the thymus gland, there are quite many in the thymus because of this process of proliferation or cell division to yield more daughter cells of the same nature. Then the second process is expression of antigen receptor genes, what we call T cell receptor. And this is very, very important because it enables the cells to kind of become functional by developing the right receptor. So the genes, remember, these are just genetic information required to generate the T cell receptor. And now the selection of the T cell receptor also is very important because it's the one that enables the T cells to recognize or to have diversity to recognize many antigens of any sort. So that is very, very critical. So we've talked about the cells dividing into many daughter cells. That is the process of proliferation. We have also the expression of antigen receptor genes, which is very important for stimulating or for development of the T cell receptors, which are also very important for T cell functions. Okay, next slide, please. Now, there is also a rare population of hematopoietic progenitor cells, and this is very critical in terms of ensuring that the T cells have attained the correct functionality from the time they develop in the bone marrow and the time they mature in the thymus region or the thymus gland. So the immature T cells, or thymocytes for that matter, we talk of them that they are differentiated by having distinct T cell receptors by a process of gene rearrangement. Now, that tells you that there must be some special proteins, what we call the combination activating genes, which gives rise to RAG1 and RAG2. These are proteins or enzymes that are important in bringing out this recombination. And this enables the T cells to keep on reorganizing or recombining its surface antigens to recognize a variety of antigens. The same synonymous with the B cells using their immunoglobulin receptors known as the B cell receptors, the BCR. Now, this process is error-prone, and some thymocytes fail to make functional T receptors, while others thymocytes make T cell receptors that are autoreactive. That tells you that there must be a process to ensure that these error-prone T cells needs to be dealt with. Otherwise, if they leave the thymus region and go into blood circulation, then they might cause this autoreactivity or unnecessary responses to the cell antigens. Next slide. Now, the majority of the T cells, or the when they are in the thymus, they develop these very important genes, alpha beta genes, which is very, very important as part of the T cell functionality. However, approximately 5% of these T cells bear a different chain, that is the gamma and the delta chain receptors. And these cells, sometimes you find them abundant in mucosal surfaces and the gut, where they kind of interact with antigens directly without being MHC restricted, meaning they do not require an antigen that is coupled with an MHC molecule for them to recognize that antigen. And this is a unique feature for gamma delta T cells. But the alpha beta T cells, where we talk about the CD4 and the CD8 cells, these are MHC restricted because they require an MHC antigen complex for them to interact with that antigen and carry out the functional process of the T cells, either releasing cytokines to activate other immune cells, and that cascades the inflammatory response. Now, the developing T cells, or the thymocytes, needs to interact with the thymus stromal cells, which are the non-hematopoietic cells, which are located on the outer region of the thymus, that is the cortex, and also they need to pass through the inner part, which is the medulla region, for these T cells to fully mature. So the sequence of events is that from the bone marrow, the T cells, or the premature T cells or pro-thymocytes, they come into the thymus gland through the outer region, that is the cortex, which is very rich in this T cell population, so that is immature T cells, and through the process of the proliferation and differentiation, they still multiply. So the cortex is highly more densely populated with premature T cells that have just come from the bone marrow. Then within the cortex, the thymocytes will move to the inner part, which is the medulla region, and this is where the full maturity of the T cells takes place. So get to note what happens in the cortex region and the medulla region of the thymus, but we'll see as we move on. The earliest developing thymocytes, they lack the expression of the co-receptors. And in that case, because they don't have an expression of either CD4 or the CD8 receptor, then on that account of lacking either of these co-receptor, we call them as double negative. So bear in mind that the double negative T cells, they are yet primitive, or the chamera in form, the way they have come on board. nothing has taken place, so they are not expressing the co-receptors yet. And remember, each cell needs to develop both receptors before retaining one as a mature T cell for that reason. So we are talking about double negative on account that they don't have the co-receptors, either CD4 or the CD8. Now, the double negative population can also be subdivided by the expression of an adhesive molecule abbreviated as the CD44 and interleukin 2 abbreviated as the CD25 receptor chain. So these are very important preliminary chemokines, which are very important in stimulating the T cells to further mature or grow into another phase of T cell maturation. So let's move on. Now, the cells that lack expression of a test molecule, that is the CD424, but expresses the interleukin 2 or the CD25, they undergo what we call beta selection. So this is one way that this cell will acquire the beta chain, which is very, very important as a surrogate marker for a progressing T cell to become fully mature T cell for performing what it's supposed to do. So this beta chain bears with the surrogate chain, that is the pre-T alpha chain, and it produces a pre-T cell receptor, which forms the complex with the CD3 molecule. If you sample all the T cells, they have this CD3 molecule as the common molecule or antigen for all the T cells. Now, this complex, we are talking about the alpha beta, leads to the survival, proliferation, and arrest during the gene rearrangement and further differentiation by upregulation and expression of both the CD4 and CD8 co-receptors. And this is important because now the cell has transitioned from being double negative to being double positive. Now, during this period where we talk about double positive, this T cell has both the CD4 and the CD8 co-receptor expressed on its surface. Okay. Now, what happens to cells that don't undergo this beta selection? They receive a signal to die by the process of apoptosis. Next slide. Now, thymocytes then migrate to the medulla to undergo negative selection. Now, they migrate from where? We are talking about going first to the cortex region, and then they move to the medulla region. Now, we can talk about the positive and the negative selection. Now, the first process is the positive selection, because within the cortex, there are some epithelial cells within the cortex of the thymus, which has MHC molecules. And these cells, while they are there, the prothymocytes, they interact with these epithelial cells. Now, if the interaction is low or it's loosely tight, at that moment, these cells are allowed to move to the medulla region. So the signal of all of the tightness is not very tight, or it's just a low interaction or low avidity with the self antigens. And that is what we call the positive selection, because without these cells even recognizing self antigens, they might not even perform the issue of differentiation between self and non-self later on. So the binding with self antigens here is a bit low, not very strong, as opposed to negative selection. Now, having said that, let me now talk about the negative selection. Now remember, in the medulla region, the cell has both co-receptors, that is the CD4 as well as the CD8 on the same cell. Now the same cell is interacted with or interacts with the resident macrophages or the dendritic cells, which bear either MHC class 1 or MHC class 2. And bear in mind that these are professional antigen presenting cells. So what happens, depending on which receptor interacts with which MHC class, you can have the signal transmitted that this double positive cell finally matures into CD4 or CD8. If, for example, MHC class 1 molecule expressed by the antigen presenting cell, be it a macrophage or a dendritic cell, interacts with that CD8 co-receptor, then that cell is signaled to mature into a CD8 cell, and the other co-receptor disappears, because now when they are mature, they only retain one co-receptor, either CD4 or a CD8. So it is kind of continuous interactions that is taking place by chance, but remember, whichever the class MHC molecule that is involved, then that double positive will yield to a single positive mature T cell. And if you look at the size for the double positive T cell, it's a little bit larger in size, but the mature ones with the single positive, meaning they are either CD4 or CD8 positive, they are a little bit smaller in size, but these are the mature T cells of either CD4 or CD8 co-receptors. And then at that time, the cell can exit from the thymus region and go into the periphery for the blood circulation. Next slide. Now this table gives you a brief summary of what we have said, that when the cells leave the bone marrow into the thymus gland, they don't have the expression of the T cell receptors, and that's why we talk about the double negative, because they are missing both the CD4 and the CD8, or they're not expressing either of those co-receptors. But with the help of the CD44, that is the adhesive molecule, and the interleukin-2, then you expect that there is also some stages within the double negative processes. And then finally, you have the formation of the pre-T cell receptor with the beta chain. And finally, you have now the rearranged receptors. And finally, the cell now occupies the double positive nature, meaning it has both CD4 and CD8. And now, once it interacts with either the MHC class 1 or MHC class 2, which are supplied by either macrophages or dendritic cells that are resident cells within the thymus region, then the interaction can either yield a CD4 or a CD8. And I've said the yielding of a CD4 depends whether it was an MHC that in class 2 that interacted with this double positive cell to yield to a T helper cell, or it was an MHC class 1 signal that interacted with the double positive to yield a CD8 cell. Next slide, please. Now we have the cortex of the thymus, as we have said, and when you look at there is the positive selection, and this gives you the picture that I've been talking about, and about the positive and the negative selection. So if you notice that in positive selection, and I said earlier on, this is where you have highly densely populated premature T cells that have even undergone proliferation to make more dotted cells. They normally die, most of them. Actually, this is where, because there are many, but again, this is where most, like 95% of these premature T cells die because they fail to meet the first requirement, that is the low binding or the low affinity with the self antigens. Now, then they move or translocate to the medulla region, which is rich in other immune cells like the dendritic cells or the macrophages, and these are very important for supplying the signal to the double positive T cell, whether it's MHC class 1 or an MHC class 2. And here, when the cells are found to strongly bind to self antigens, then these cells are considered to be autoreactive, and for that reason, they might also be given the signal to die through apoptosis, and then you have only the cells that are less reactive or less binding to self antigens, leaving the blood circulation into bringing the thymus into the blood circulation. So if somebody will ask you what is the positive selection, remember this is the first process by which the prothymocytes interact with self antigen supplied by the cortical region, that is the epithelial cells, and then they need to be showing low avidity to these particular self antigens. And then those cells that have this low avidity or that have shown the low interaction with the self antigens, they are allowed to go into the medulla region. And now that is the positive selection. So positive selection is not to release the mature T cells into blood circulation, but rather to release them to the medulla region. So in the medulla region, the T cells undergo further testing by interacting with an MHC class 1 or MHC class 2 supplied by antigen presenting cells. Specifically, you have either the macrophages or the dendritic cells. Now, those cells that are found strongly binding with the self antigens, they are not allowed to leave the medulla region because they are going to autoreactive. So they must die through the process of apoptosis. And in that way, you find these mature cells that are not binding strongly to self antigens, they're the ones that are allowed to go into the blood circulation. Next slide. Now, what is the role of the thymus? We have said it has the two lobes or bilobes with lymphocyte precursors, and I've said these are basically the prothymocytes that have just left the bone marrow, and now they're coming as part of the process for development. And these are the ones that mature into T cells. So once mature, the T cells immigrate from the thymus and they constitute the peripheral T cell repertoire responsible for directing many cell-mediated immune responses. So the summary is that the role of the thymus is to allow for development of the T cells from their immature state to fully mature state. Next slide. Now, we may not finish discussing about the T cells without looking at the critical surface markers. Now, there is the system of differentiating the T cells, which is utilizing the cluster of differentiation abbreviated as CD. And these are special proteins that you can find on the T cells right from the time they mature, they leave the bone marrow and the time they mature. So meaning some antigens are expressed earlier in life, but they disappear as the cells mature, while some are acquired towards the maturity, but they are not there at the beginning. You have even seen the expression of the T cell receptor, for example. So this cluster of differentiation, or the CP, was provided as the discovery went on. For example, can identify or bind with specific biomarkers and give you a signal that you can read through the flow cytometry. Now we have the T cell receptor, which is very important for interacting with an antigen. And the T cell receptor is like the fingers within the hand, or which is used for grasping. So the T cell receptor is the one that interacts with an antigen that is bound with an MHC molecule. Whether it's MHC class 1, then that becomes a target by the CD8. If it's an MHC class 2, with an MHC molecule, now it becomes a target by the CD4. And that's why we talk about the T cells are MHC restricted, because they see an antigen once it has been coupled with an MHC molecule. Next slide. Now, the T cell receptor, as we have said, it is important for interacting with an antigen, and this has ability to recombine during the lymphocyte maturation, and that gives it flexibility to recognize various antigens, and this is the property that is also shared with the B cells through their B cell receptor. Now, this T cell receptor is a heterodimer consisting of two non-identical polypeptide chains linked together by disulfide bonds. We have talked about the beta and the alpha chains, but remember, some special T cells, they have the delta and the gamma, including the epsilon chains of the CD3 molecule. So this gives it another additional. Now, the complex T cell receptor with the CD3 makes contact with both the antigen and the MHC glycoprotein. What we are saying here is that there is always the first signal. Yes, we have the T cell receptor, which is always the first one to interact with an antigen, but yet there are other important chains. For example, the CD3, which has these additional smaller chains like the delta, gamma, and epsilon chains. Now that makes the binding so tight. If you consider you having one finger or two fingers, you cannot compare the grip of 2 fingers with 5 fingers. The difference is there. And that's why when we talk about the complex, that tells you there are many molecules that are involved, so that the interaction between an antigen MHC complex with the T cell receptor is very tight, and that is enough to activate the T cells to perform other functions like secreting cytokines to recruit other immune cells, or even secreting special cytokines to activate the B cells to produce antibodies that are very important for dealing with either viral or bacterial infections. Next slide. Now, this is interaction between an antigen presenting cell APC, which has expressed MHC molecule with an antigen, and then interacting with a T cell. Now, like I've said, the CD45 is a common surface antigen with all white blood cells. Then there's T cells, they have the CD3 molecule, which is common with them, either CD4 or the CD8, they have the CD3 molecule. And then the genes that are very critical, part of the CD3, the epsilon, the gamma, and the delta, including the alpha and beta genes. So these genes provide the basis for tight interaction between an antigen MHC complex with a T cell receptor. And that gives enough signal, what we call a signal transduction, that the T cells now becomes activated and produces cytokines for the next course of immunological action. So that's basically what we are talking about, what you can expect to find on the surface of a mature T cell. You have a T cell receptor, you have the CD3 molecule, together with the combination of other chains that are very important. Next slide. Now, subpopulation of T cells. think you have been even exposed to these cells before. It's not the first time you are hearing. Like, I know the times we have had the HIV/AIDS, people were using this as the biomarkers to look at the nature of or staging of HIV. Now you look at the CD8, or it is called the cytotoxic T cells. These are very important because they recognize foreign epitopes when they are in association with MHC class 1. Now you can link up with the origin of the CD8 from the or within the thymus region by either interacting with MHC class 1 or MHC class 2 provided by antigen presenting cells, mostly the dendritic cells or the macrophages. Then we have also the helper T lymphocytes or the helper T cells with the CD4 receptor. This is very important to recognize epitopes or antigens that are in association with an MHC class 2. And this is what we talk about the MHC. T cells are MHC restricted because they have specific antigens they recognize depending on which MHC is involved for presenting this antigen. Next slide. The cytotoxic T lymphocytes, as we know them, the CD8 cells, they cause killing by lysing the target cells, and this includes the virally infected cells as well as the tumor cells. So the work of the CD8 cells is to monitor the presence of virally infected cells or the tumor cells and lyse them by releasing certain special proteins. We call them bufferin, which polymerizes around the target cell, and the enzymes, which are proteolytic enzymes, which pokes holes on the target cell and cause that infiltration of calcium ions and the water imbalance that causes the cell to lyse. So they recognize the epitopes or antigens that are in association with an MHC class 1 we have talked about. The mechanism of killing, I've mentioned this by releasing bufferin, that is a protein that polymerizes around the cell membrane of the target cell, and also the enzymes, which are degrading enzymes or essentially by macromolecules that pokes holes on the target cell, and that causes lysing. Next slide. The T helper cells, as we know them, they play a very key role in activating or making other cells proliferate, differentiate into various functional units. If it's the B cells, the T helper cells can activate B cells to produce antibodies, which are very key in destroying ingested microbes by various processes. We talk about opsonization, neutralization, and so forth. That will be learned under different mechanism, where you look at the antibody-dependent cell cytotoxicity utilized by either macrophages, neutrophils, and natural killer cells. So you can read about that. So the origin of this antibody that is utilized during the antibody-dependent cell cytotoxicity comes by the fact that the B cells have been activated and now they have produced antibodies. But where the activation came from? By the T helper cells. However, B cells can still interact with an antigen directly without being activated by the T helper cells. And we talk about the T-dependent and the T-independent B cell activation. So under B cell, you can learn about that. Now, this subset of these T helper cells is further given different subsets or subclasses. We talk about the T helper type 1 and the T helper type 2. So let's move on and see what are the differences between the T helper cells. Now, the T helper cells, we talked about earlier on, they recognize an MHC that is interacting with MHC class 2, interacting with an antigen. So that becomes a target by the T helper cells. Now, which cells do you know that have this MHC class 2. Antigen presenting cells, they are the ones that usually have this MHC class 2 expression. That is the macrophages, the dendritic cells, the B cells. And whenever, for example, in case of Mycobacterium tuberculosis, you find the macrophages are infected. So more and more macrophages, as they come to the site of infection, sometimes they even get infected. And that causes the neuroma formation, especially with the TB patients. But just bear in mind that the T helper cells, they recognize an antigen that is coupled with an MHC class 2. So I was giving an example, the cells that have this MHC class 2. Now, the helper T cells, they activate B cells to produce antibodies, and that is through the circulation of cytokines. I know cytokine interleukin 4 and interleukin 5. These are some of the key cytokines produced by this T helper type 2 to activate B cells to produce antibodies. Now, subsets of T helper cells, let's look at them in detail in the next slide, please. We have the T helper type 1, and their main function is to secrete the following cytokines. We have the interferon gamma, which is very important in activating macrophages to become more effective at killing phagocytosed microbes, suppress the development of T helper type 2. So sometimes one subpopulation of T cell can suppress the other population of T cell, and this one example that we have just mentioned. So interleukin 2 is also released by T helper type 1, which stimulates the survival and proliferation of T cells, called the T cell growth factor. So earlier on, we even talked about this interleukin 2 at the time of T cell development. But now that we have already the mature T helper cells, they can also expedite the process of T cell development by releasing this cytokine. So that is the beauty about the immunological responses, that you have more than one cell secreting the same type of interleukin for purposes of expediting immunological responses, because you know the pathogens are high rate of replication. So the immune system must act so quickly. So it's good that more than one type of cell population can release this important cytokine that is required to activate other cells to perform its other functions. We have also the tumor necrosis factor as one of the cytokines produced by the T helper type 1, which stimulates the recruitment of neutrophils and monocytes to the site of infection. And this is very, very important, especially during acute infections. We have also the interleukin 3, which promotes expansion and the immature marrow progenitors of blood cells. So it is important also that the bone marrow is stimulated to produce more cells as the demand might be, especially like the time of infection or injury. And this is the work of the T helper type 1. So the other cytokine that is produced by the T helper 1, we have the granulocyte monocyte colony stimulating factor, which acts on the bone marrow progenitors to increase production of neutrophils as well as monocytes. Next slide, please. Now, the T helper type 1 based immune reaction. So we have seen that the T helper type 1, they stimulate the phagocytic cells to eliminate the ingested microbes. And what are these phagocytic cells? We talk about the macrophages, we talk about the neutrophils, we talk about the dendritic cells. These are phagocytic cells. But bear in mind, we have professional phagocytic cells and we have non-professional. And when we talk about non-professional, even the B cells are not professional, but they can still phagocytose by the process called receptor mediated endocytosis. But you can learn this under the B cells. We have also the release of interferon gamma, which is the main T helper type 1 cytokine, and usually it's important for activating macrophages, especially during the early acute infections and all the chronic infections where you find, for example, there is need for recruitment of new immune cells. If others get infected or they die, then you need to have continuous supply. Then we have also the regulation of other immune cells. This population, we call them T regulatory cells or the T suppressor cells. So this is very important because it regulates both the CD4 and the CD8 cells. Okay, next slide. Now, let's look at the other subpopulation of T type 1 T helper cells. We have the T helper type 2, which is important in secreting the following cytokines, interleukin 4, which is important in activating naive B cells to produce antibodies. Now, specifically when it is an allergen, then the B cells is stimulated to produce one specific immunoglobulin, and that is immunoglobulin E, that it finds its fate being bound with Fc epsilon receptor that are expressed by the mast cells. So this causes allergic responses later when you have the second encounter with the same allergen. Now, interleukin 5 affects the mast cells, and usually what happens, sometimes the two cytokines can activate one cell synergistically, that is interleukin 4 and interleukin 5, and this happens with hypersensitive reaction type 1, where you find the production of immunoglobulin E whenever you have the two cytokines involved to activate the B cells. Now, where do this come from? And I said this is now the functional entity of the activated T cells. So if it's a T helper type 2, then you expect these cytokines will be abundant. So if you sample a sample or a patient with allergic responses, you can find the elevation of these interleukins in the blood, which is important in secreting or in the synthesis of the acute phase protein during acute infections. That is a process that happens with the liver cells. And also the interleukin 10, which inhibits macrophages and also sometimes suppresses the T helper type 1 production. You remember the other cells we talked about inhibiting the T helper type 2, but here this interleukin 10 inhibits the T helper type 1 function. Then we have also the production of or secretion of the interleukin 3 and the granulocyte monocyte colony stimulating factors that are concerned with the issue of the bone marrow cell development. Next slide. Next slide, please. Yes, the T helper type 2 response provides the B cell by activating them to produce antibodies that are very critical during the antibody-mediated cell immune responses. And these antibodies are required especially for dealing with extracellular pathogens. Now, these are the pathogens you find freely circulating within the blood system without necessarily being intracellular, but these are extracellular pathogens. Now, the type 2 T helper type 2 cytokines include interleukin 4, interleukin 5, and interleukin 13. Next slide. Yes, we mentioned this briefly. The regulatory T cells in other books earlier on, they were called the T suppressor cells. These express the CD4, the CD25, and the FOXP3 proteins. If you look at their surface markers, these are the antigens you find being expressed by the regulatory T cells. Their role is to regulate the activation or affect the function of other T cells. So once, if it's a CD4, then all the cytokines that are released by CD4, by the fact that this is regulated, that CD4 cannot continue to secrete or function. Same thing applies with the CD8, and this is why we talk about the regulation of the immune system to avoid highlighted or exaggerated immune responses or hypersensitivity. And these regulatory T cells, they are very important in maintaining tolerance to self-antigens. If, for example, the CD8 is found to be autoreactive, it has to be regulated so that it does not cause harm to the cell or the cell antigens or to the host, that is. Next slide, as we come to a closure. Now, in summary, we have looked at this positive and the negative selection. And if you remember, we mentioned about the immature thymocytes or thymocytes that have come from the bone marrow and have come to the thymus gland, where they first go or come to the cortex region, where they undergo proliferation, differentiation into many daughter cells of the same type. And then there they have to go this process of positive selection within the cortical region, meaning they need to show that they can interact with low affinity with the self antigens, and then they can be allowed to move from the cortical area or cortex to the medullary region. And that is very, very important. And that is what we call as the positive selection. Now, the negative selection within the medullary region of the thymus, they need to be tested by MHC class 1 because this cell is already a double positive because it has the CD4 and the CD8 co-receptor at the same time. So if they found like they can interact with an MHC class 1 or 2, yes, they can be allowed. But the strength of interaction